All right, folks, I wanted to make a quick video just to discuss slope fields. So differential equations are complex enough that most of them you can't solve analytically, meaning we can't just do like hand calculus and find the solution. So what we have are techniques to estimate solutions numerically and visually. And so slope fields are a technique to estimate the solution to a differential equation visually. So here's what they look like. The idea is this. Remember that our most basic understanding of a derivative was that it is a slope, right? So y prime, or dy dx, is a slope. So if you have a first order differential equation where you can isolate the y prime, you can interpret that in a way that you can look at any point in the coordinate plane, and this is like a formula telling you what to do with that coordinate to find the slope at that point. So the idea is that in this case, so y prime is x plus y, which means I can take any coordinate in the coordinate plane, like for example 0, 1, and all I have to do is add x to y. So 0 plus 1 is 1, and I can draw in a little slope there. So if I do that with enough points in the coordinate plane, we start to get this picture of the behavior of a family of functions, right? So remember that a solution to a differential equation is a function. So a differential equation is an equation that involves an unknown function and its derivative, or one or more of its derivative. So what we're looking for is y. That's our unknown function. And when you solve a differential equation, you get a family of functions. And sometimes, if you're given an initial value, like in this case, y of 0 equals 1, that specifies for you the specific function in the family that you're looking for. So in this case, I could go, okay, 0, 1 is right here. And when we look at this, what I want you to think of is, think of that point as a ping pong ball, and think of what we're looking at in terms of the slope field as a river and a current. And what would that ping pong ball do in that current? So we can kind of sketch in the behavior that we think would happen. When you draw in your curve, you just want to be sure you're not ever going against the grain. So we don't want to go against the grain like that. You kind of want to go with the flow. And same thing in the other direction. We're going to go with the flow. And there, we get a general idea of what the solution curve would look like for that initial value. Okay? So drawing slope fields by hand is kind of a pain, because you could literally draw this for any number of coordinates, right? And if you do it for too many, then you're just going to get a block of color that is not helpful. But too few, and you don't get an idea of what the curve looks like. So I wanted to illustrate that in Geogebra. So here's the same function, which is y prime equals x plus y. I can change the density to give you an idea what I'm talking about. So if I increase the density, we get more of an idea. But if I increase it too much, it becomes kind of hard to tell. There's too much detail, right? And it also lets you increase the length of these little tick marks. But too long or too short, and it becomes hard to understand what the behavior is. And then this lets me enter in different initial values to get different solutions. So there's a couple different solution curves from the family of functions with different initial values. All right, so let's do a couple examples. What you might see. All right, so sketch a direction field for the differential equation y prime equals x squared plus y squared minus 1. And then use part A to sketch a solution curve that passes through the origin. I'm just going to do a few points, but let's look over here. So we'll do my xy coordinate, and then what does y prime come out to be? All right, well, let's start with the origin. So 0, 0, and we're doing 0 squared plus 0 squared minus 1, so that would be negative 1, right? Let's see, let's do 1, 0, so 1 squared plus 0 squared minus 1 is 0. Do 0, 1, also going to get 0. Negative 1, 0. Negative 1 squared plus 0 squared minus 1 is still 0. 0, negative 1, still 0. What about 1, 1? So 1 squared plus 1 squared minus 1, you're going to get 1. Same thing for all combinations of 1s. Whoops. And then let's see, like, what about 0, 2 or 2, 0? So 2 squared is 4, minus 1 is 3. So any combination of 2's and 0's, you're going to get 3. And then what about like the 2, 2 combinations? 2 squared is 4 plus 2 squared. So 4 plus 4 is 8, minus 1 is 7. Okay, so if we go through this, we can now kind of sketch in our little tick marks. So 0, 0, negative 1. And then we have zeros here, 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 here. And then 1, 1. Right? And so on. So kind of tedious to do by hand. You may have to do these by hand, but let's look at what this would look like in our Geogebra setting. So let me unclick these, and this should let me edit this. So if I do x squared plus y squared minus 1. Cool, there we go. So that gives us a little bit of a better picture of what's going on there. And then if I want my solution to go through the origin, let's see, something like that. So you can kind of see how this goes with the flow. Just view the tick marks like the current of a river from a bird's eye view. All right. I'm going to do one more example. So for a long time, I was like, yeah, we're doing these slope fields. They'll never put one on the AP exam. And then in 2016, they put one on the exam. I had never seen it before, but they actually had a slope field on the exam, and this was it. So says on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. So we have our formula for what to do to find the slope at each coordinate. All right, so I just want to do the same thing. For those 6 coordinates, I'm going to make a table. So on the left, I'll put the coordinate, and on the right, I'm going to put sorry, this isn't updating. All right, so at the left, I'm going to put the coordinate, and on the right, I'm going to put the slope. So for those 6 points, let's see, what do we have? We got 0, 0, and it's y squared over x minus 1. So 0 squared over negative 1 is 0. Then we have 0, 1. So 1 squared over negative 1 is negative 1. Then we have 0, 2. So 2 squared, which is 4 over negative 1, would be negative 4. Great, and then we have 2, 0. So that's 0 squared over 1, which is still 0. Then we have, what is that, 2, 1. So, oh boy, 1 squared over 2 minus 1. So that's 1. Oops. Oh, and I skipped, sorry, 1, 1. Which is going to be 1 squared over 1 minus 1, which is undefined, which is going to give us a vertical slope there. Okay. So here's what this is looking like. So at 0, 0, we have a slope of 0. 0, 1, we have a slope of negative 1. 0, 2, we have a slope of negative 4. And they're not picky. You just need to make them relative to each other. So they're not going to like take a protractor and measure that your slope is actually negative 1. But what you want to see is that my slope of negative 4 is steeper than my slope of negative 1, right? All right. So 2, 0, 0, 2, 1, 1, 1, 1, undefined, so I'm going to have a vertical slope there. The last part of this, let the particular solution at the given differential equation with initial condition f of 2 equals 3. Write an equation for the line tangent to the graph y equals f of x at x equals 2. Use your equation to approximate f of 2.1. All right. So for this one, remember what we need to be able to write an equation of a tangent line is a point. So we need a point and a slope. They give us the point. The point they give us is 2, 3. And the slope we can get from our differential equation formula, right? So we're looking at 2, 3. dy dx at 2, 3 will just be 3 squared over 2 minus 1, which is 9 over 1, which is 9. So the equation of my tangent line is going to be y minus the y coordinate equals the slope times x minus the x coordinate. So x minus 2. I am going to put this one in slope-intercept form because they're asking us to make an estimate with it, and it's just going to be a little bit easier. So my slope-intercept form is y equals 9x minus 15. And I'm going to call it L of x, meaning the linearization at that point. And they want us to estimate f of 2.1. So all we need to do to estimate what's going on at 2.1 is replace our x with 2.1. So this is going to give us 18.2 minus 15, which is 3.2. There's our answer. All right, folks. Hope it helped. See you soon, hopefully.